What do we want to go over? Put it in the chat, say, raise your hand, shout it out.
Just here for whatever you give.
How y'all feeling about polarity and stuff like that? Stuff's all right.
I think that's the easiest chapter that we have this exam. So I think our time would be best spent either on chapter 5 gases or chapter 6 thermochemistry. What do y'all think? I'll agree with that. Okay, so which one do you want to do? Chapter 6 thermochemistry. We got one person for gases. Well, we got. Take a vote, guys. Thermochemistry. We got. Chapter 6. All right, we'll do. Looks like we have more people that want chapter 6. So guess what we'll do? Chapter 6. Okay, let's see. Let me stop sharing my screen really quick to make sure I can clear out all the stuff.
All right, just sent.
Good. So I'll show you the problems that we had already done, which are going to be on our YouTube channel, if you want to check those out. So we started, thermochemistry starts off at question 44, and pretty much everything after that is thermochemistry. So there's around maybe 20 thermochemistry questions on this, which encompass everything you should know how to do for the exam. Don't memorize step-by-step processes, understand how you do it and why you do it, okay? So we've already done this. All these, you can find them on the YouTube channel.
Once again, that's team entropy, TEAM space entropy, ENTROPY.
Precise. All right. Same thing with number 50. So right now we're going to do number 52. So I'll give you all 3 minutes to work on number 52. This is a hint. This is using Hess's law. Y'all know what Hess's law is?
Yeah. Don't remember it. That's what we're here.
Yeah, so go ahead and try number 52. Give you 3 minutes. Calculate delta H for this reaction where calcium and oxygen go to carbon, or oh, my bad. Calcium, oxygen, carbon dioxide go to calcium carbonate.
Se acaba a las 6. Acaba a las 6.
Es que dice.
Two more minutes.
Summation of the mechanistic reactions to
Something that big. All right.
way to calculate the overall delta H reaction. Given given the overall step-by-step mechanisms.
Memorize that and you're gonna say.
Hey, Rich, have you guys sent out the PDF for this?
Yeah, if you're in the group me, scroll up. I sent it like 2 weeks ago. Should
Oh,
say
this
like
is the one?
chemistry 1 exam 2 review.
Okay.
All right. Hopefully we're able to finish. If not, we'll go and get started now. So, like I said, if we can't access it, what do you suggest?
Try opening it on your computer, because GroupMe files on your phone are kind of weird. Otherwise, I'll email it to you right now. I think I already did. But yeah, I can do it again, no problem.
Okay, perfect. So, all right, so we told you, we gave you a big hint that we should be using Hess's law to answer this question, right? And what is a good definition of Hess's law?
Hess's law is basically a way to calculate the overall delta H of a reaction given all of like the mechanisms. So what does that mean? Basically, you'll be given like a goal equation, like an end like product, and then they'll give you like all of the individual like reactions, like the step-by-step way on how to get to that goal equation. And they'll give you the delta H for each one of those individual steps. Hess's law basically puts together all of those individual steps to give you like a comprehensive total delta H value.
Yeah, so this is the goal equation. The 2 NOCl is converted to nitrogen gas, oxygen gas, and chlorine gas. So that's our goal equation. And we have to manipulate these 2 equations in order to get to this equation. And one thing we have to note is that if whatever we do to this equation, whether we flip it, we multiply it through by a number, we have to do to this value over here. All right, so it says that we want NOCl on the left side. There's only NOCl. NOCl only appears one time in both of these equations, and it's the one on the bottom right. And we want it on the reactant side. Right here, it's on the product side. So we need to do what to that reaction? We need to flip it, right? So we're gonna flip it. And the way we flip it and show that we're doing it is, I just normally rewrite it. So NOCl gas is now converted to NO gas and half of a mole of chlorine gas. All right, and if we flip that reaction, we need to flip this one as well. When we say flip that, we mean change the sign of it. So if it's negative, you change it to a positive. If it was positive to begin with, you would change it to a negative. So in this case, we just multiply it by -1. So pretty much every time you flip a reaction, just multiply it by -1. So that gives us our NOCl on the left side. What do we also know that in this equation, we have 2 moles of NOCl, right? Which means we need to multiply this bottom equation by 2 to all the way through. So that would give us 2 NOCl, 2 NO, and 2 times 1/2 is just 1. And if we did that, we also need to multiply this value of delta H by 2, right? So we already multiplied it by -1. So it'd be -1 times 2, which is just -2. So it's almost as if you just decided to multiply this by -2. All right. Now for the bottom equation, we see in the goal equation, we have nitrogen gas, oxygen gas, and chlorine gas on the right side, on the product side. But in this first equation, they put the nitrogen and oxygen in the the reactant side, and we need to flip it in order to get it to the product side. So you just do, and it's also important to note that the coefficients of nitrogen and oxygen in the goal equation are 1. In this case, they are 1/2. So we should multiply it by what? What? You should multiply it by, if we want to get from 1/2 to 1. So you multiply it by 2, right? So we're gonna multiply it by 2. And we're gonna flip it, so we're pretty much multiplying it by -2. So that does, and then to rewrite it, you would do 2NO goes to 1 mole of N2 plus 1 mole of O2. All right. Now is the easy part. You just cross everything off that cancels out on each side. So we look at NOCl. There's no NOCl on the right side of any of these equations. So therefore we cannot cancel NOCl out. Same thing for chlorine. There's no chlorine on the left side. It has to be on the opposite side for it to cancel out. So we can't cancel out chlorine, and same thing with nitrogen and oxygen, but we can cancel out the 2 NOs on each side. All right. It's important to note that if we had 1 NO there and 2 NOs there, you can't cancel out the NOs like we did here. You would be able to cancel out one of the NOs, nitrogen monoxides, and you would still be left with 1 on the right side, right? So it's important that you recognize that you have to multiply this one by 2, so that way you can give that proper canceling out. So your overall equation would be 2 NOCl produces chlorine gas, nitrogen gas, and oxygen gas, which is what our goal equation was here. So now what we do is just add up all the delta H's, and we make sure to include the changes that we made to them. So it would be 90.3 times -2 plus -38.6 times -2, and you should get, so this is equal to delta H. This is going to be -180.6 kilojoules plus 77.2, and if you add those up, you get -103.4 kilojoules per mole. Unit should be kilojoules per mole. I just didn't write the mole part here, so it should be mole there. Right, so that's the basic application of Hess's law. This is probably an easier question using Hess's law. There's a lot more difficult problems that it can get way more difficult. I'll show you one. Number 54, there's a lot to think about here. And for time's sake, because this is just exactly what we did, just but on a larger scale, I'm gonna let y'all do this one at home. And maybe you can come back and check your answer on Thursday. But let's go to something different, okay? So let's see. All right, let's do number 55. So it's saying, make any changes needed in each of the following equations so that the enthalpy change is equal to the enthalpy of formation for the compound. All right. So what is the definition of enthalpy of formation? So enthalpy of formation is defined as the heat associated to make 1 molar product, whatever that product is, from its element, the elemental form. All right, so let's look at case A. In case A, our product is sodium chloride. That's a compound, right? And everything before that should be in its elemental form. And we should also have 1 molar product as well, right? So if this said 2 NaCl, that would be a red flag. We should only have, the coefficient for that should only be 1, because we're only forming 1 molar product. So is there any changes that need to be made to 55A? sodium solid and chlorine gas.
Isn't chlorine diatomic?
Chlorine is diatomic, so in its elemental form, chlorine is found as Cl2. So we have to go ahead and rewrite this. The correct way would be Cl2 gas plus sodium solid goes to sodium chloride solid. That's the best, that's how you should do it.
Does it not matter that there's not two chlorine on the other side?
What was that?
Does it not matter that there's-
Oh, yeah, you're right. So what we have to do is balance it. So you would do 1/2 there as the coefficient to make sure that you have, it's like cutting it in half. You have 1 chlorine on this side, 1 chlorine on this side. So that's how you would balance that one. And I know it's weird because you start to see fractions as the coefficients, but that's what you're gonna see when you're talking about heats of formation. And I believe that's what we saw earlier when we did that Hess's law problem. We saw a couple, half coefficients. All right. For B, what needs to change?
Hydrogen,
What was that?
the hydrogen.
Okay, so hydrogen is diatomic, so it needs to go to H2, and anything else?
Is it only 1 mole, right?
1 mole of product, yeah.
2 moles of hydrogen.
So you're on the right track, but we have to, the thing that I think we're missing is that we have to flip this reaction around, because we're trying to form heats of formation would be to form a single compound, not multiple things. So the correct heats of formation would show that we flip this around and we're forming water. So the first thing that we would have to do is flip it, so you would get 2Hg plus 1/2 O2 gas yields H2O gas. So that should be the first thing that we thought of, because we realized that heats of formation is the amount of heat required to make 1 mole of a specific compound, right? And in this case, our specific compound is water. Hydrogen and oxygen would be the things that go into making water from its elemental form. So we want 1 mole of water, and we need everything on the reactant side to be in its elemental form. So one person mentioned that we need H2. And we put an H2 there, that means we don't need that 2 coefficient anymore. And we put H2 because hydrogen is diatomic, it exists as H2, you're never gonna find a single hydrogen atom by itself. So this would be the correct answer for 55. So for 55C, I'll let you go ahead and give you 1 minute to work on that one. See if what y'all get. Yeah. All right, what needs to be done for C?
There's like a missing state symbol, and then there's like an equal sign instead of the arrow.
Yeah, so the equal sign is my bad, that should have been an arrow. On Word, you do 2 equal sign and a greater than symbol, and it gives you the arrow. I must have not done the other equal sign and the greater than arrow. So let's pretend that's an arrow. And you said state of matter for hydrogen, right? So 1/2, it should be 1/2 N2G, 3/2 H2 gas gives you 1 mole. What's the name of this product? Ammonia, right? Yeah. Okay, so that's the only change that should be made. It should never be an equal sign. Whenever we do chemical reactions, it's always arrows. So that was just my error. And if you ever saw an equal sign on a test, just assume it's an arrow. Unless it's something, an equation. All right, what about the D?
Yeah, 2 moles.
So 2 moles of product is the first thing that we see is wrong, right? Because it's important that a heat of formation reaction only produces 1 mole of product. So we should change that from what it is to H2 gas plus F2 gas gives HF gas. And we need to make sure that they're balanced, right? So we should put coefficients of what in front of H2 and F2? 1/2, right? 1/2, 1/2. That's how you would balance that one. So once you get the hang of these, you're definitely going to get a question like this on the test. I'm pretty sure I saw it the last 3 semesters on the test. So make sure you know how to do this. And make sure you know the rules of this. So you should form 1 mole of product. Everything should be in its elemental state. And coefficients should be matching up, right? It should be balanced. All right. For a fun time, let's do this one I just wrote up here. So PbBr2 goes to Br gas and lead solid. Was it?
Or was this to just share, or you were giving us time to do it, or?
Yeah, just tell me what needs to be changed.
The bromine isn't balanced,
Okay, so that's one thing.
and then it's, yeah,
We should flip it, right? Because right now this is, I don't remember the term, but you're breaking down a compound into its elements. Maybe I don't know that off the top of my head. So what it should be
Decomposition reaction.
sounds about right. So Br plus PbS gives you PbR2. Solid. And what did we say? We also said Br is not balanced. So how do we balance that?
It's
To where?
naturally diatomic.
It's diatomic, right? So it exists as bromine Br2. So if you put a coefficient of 2 there, that would be wrong because this Br is not in its elemental form. It would be Br2 in its elemental form. And is that it? That's it? Let's see. Is that it? Is Br2 a gas in its natural state? Yeah, so I put this up here. It's on the PDF for you as well. It gives you all the natural states of your diatomic elements. We see that iodine in its natural state is a solid, chlorine is a gas, and bromine is a liquid, not a metal. So with that, we should change the physical state of bromine to liquid. And that's it. Next one is an interesting one. All right. 56. I'll give you 3 minutes to work on this one. Go ahead and try that.
Bro, not gonna lie, today was the first day my teacher gone over this stuff.
Your professor.
I've been told you, spaghetti, bro. I'm in the dumps.
That's crazy.
Bro said his name like the Serengeti Desert, bro.
Sarah.
Come on, Rich, calm down, calm down.
That is crazy. Well,
It's like he says we'll probably be done with all the topics, hopefully by the test time. I'm like, what?
yeah, you should probably read the textbook if you haven't already. Because there's no guarantee he's going to get through all of it. He might say, this is not that important, but it's on the test.
Right.
All right, so what's the equation that we should use to solve this problem? So we're asked to find the delta H of formation of copper 2 oxide. We're given the delta H of that reaction, right? So we're given that here. Then we're given the heat of formation of copper 1 oxide, also known as Cooper's oxide. Okay. So there's this equation. If your professor hasn't gone over it, you probably don't know it. It's delta, the heat of the reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. All right, so let's start off with the, I guess, the far left side. We're already given the heat, the delta H of reaction, so we can plug that in here. So negative 146 kilojoules. And the sum of the heats of formation of the products is just all the heats of formation on the right side of the equation. And we're given that we're asked to find this part here. So that's going to be our X. So delta H of copper 2 oxide is our X value. And you also have to bring in your coefficients. So because we're forming 2 moles of CuO, then we need to put a 2 with the X. All right. So you make sure you carry your coefficients. So that's the first part. And the second part is the sum of the heats of formation of the reactants. it tells us that the heat of formation of copper 1 oxide is negative 168.6. Right, so negative 168.6 kilojoules. And that is, and we also have to do that, that of oxygen, right? And make sure you carry your coefficients down. As we see, there's a coefficient of 1 here for Cu2O, right? So we don't need to put anything here in this case. But what is the heat of formation of oxygen? It didn't give it to us. This is something that we should know. 0. Anything that is in its elemental form, so oxygen, O2, Br2, all of those, their heats of formation is 0 because the idea behind heats of formation is to form a compound from its elements. If you try to form oxygen gas, O2, from its element would be O2, right? So the heat associated to go from one thing, O2, to the same thing is 0, right? It's the same exact thing. So there's 0 heats of formation for things that are in its natural state. So plus 0. And if you put that into your calculator, you should get that X is equal to negative 157 kilojoules. And this is equal to the delta H of formation of copper 2 oxide. So I didn't show you all the algebraic manipulation and stuff. I figured I don't need to waste time on that, but you're just solving for X. All right, and that's your answer. Any questions on that? No questions. Any questions on Zoom? No in the chat. Yes in the chat if you have a question. No in the chat if you're good. Awesome. Thank you, Daniel. Thank you, whoever else, Sydney. Thank you. All right. Let's skip 57 because 57 is very similar to that. So again, this is being recorded and we'll try to post this. When are we going to post this, Rich?
By tomorrow, probably.
So try number 57 on your own. If you didn't understand this, maybe you can watch it again on our YouTube channel. We'll go on to something different. All right, number 58 is talking about heat capacity, which is our Q equals MC delta T equation, right? Every time you think of heat capacity, you should probably ring a bell that the equation you might be using is your Q equals MC delta T. All right. So it's asked, or 58A says, calculate the energy required to raise the temperature of 150 grams of silver from 273 to 298 Kelvin. So give you some time for that. Give you 2 minutes. And it's also important to note that, so right now it's 0.24 joules per gram times degrees Celsius. This is equal to, it's the exact same thing if it was Kelvin. So it's equal to 0.24 joules per gram times degree Kelvin. There's no difference in that, okay? So it's interchangeable, Celsius and Kelvin.
So you don't need to convert it.
No, because a change in a change of 1 degree in Kelvin is equal to a change in 1 degree in Celsius, because it's just multiplying, it's just adding 273 to the number. It's only specific to these specific heat problems, okay? Don't go telling Dr. Armand that I said you don't need to convert to Kelvin when you're doing gas law problems, all right?
Or you can blame it on him, it's fine.
You'll be like, Dylan did not say that. And there's a recording for proof. Coming back over. What is that? All right, let's do 30 more seconds. Pretty soon you'll realize that these are the problems that you're hoping that you get on the test, because in terms of thermochemistry, this is probably as basic as it gets. I guess it could be an easier one with the internal energy of a system. But this is down there. All right, so what's the equation we're using?
Q equals MC change.
Yeah, Q equals MC delta T, or as some people like to say, Q equals MCAT. I sure hope you know how to use this equation, because guess what? It's going to be on your MCAT. I'm not even lying. So it's asking us to calculate the energy required to raise the temperature of 150 grams of silver from 273 Kelvin to 298 Kelvin. So what we can do is we're looking for what variable? Q, right? Because it's asking us for the energy required, and that's also known as the heat required. It's interchangeable, okay? So we realize that we have the mass, we're given the specific heat in this first part, right? And we need delta T to figure out the Q, right? So delta T is equal to final temperature, T final, minus the initial temperature, so TI. This, plugging everything in, it goes from the final temperature 298, the initial temperature is 273, which is a difference of some number of 25. 25 degrees Kelvin. It's a change of 25 degrees Kelvin, or you can say it's a change of 25 degrees Celsius. They're both the same. Okay. So plugging everything in, we get Q is equal to the mass, which was 150 grams. The specific heat of silver we said is 0.24 joules per gram degree Celsius or Kelvin. It doesn't matter. And the change in temperature was 25 degrees Celsius or Kelvin, right? So Q, after multiplying that out, is 900 joules. It didn't say convert to kilojoules or anything, so whether you put, if it doesn't say what units it wants the answer in, if you do 900 joules or 0.9 kilojoules, you should get the answer correct on the test, okay? So that would be the answer for number 58A. All right. What about calculating the energy required to raise the temperature of 1 mole of silver by 1 gram, or no, by 1 degree Celsius? So what is our change in temperature for this process? 1, right? So it's literally saying raise the temperature by 1 degree Celsius. So that's a change of 1 degree. So this is equal to our delta T. And 1 mole of silver, you might be thinking, our MC delta T equation only, it says mass, we can't plug in moles here because if you plugged in the amount of moles here, you would have to change the specific heat, right? Because the specific heat is the amount of energy required to change 1 gram of substance by 1 degree Celsius, not 1 mole of substance by 1 degree Celsius. So what should we do for this problem? If we're given, it's asking about 1 mole of silver. So 1 mole of silver, just looking at the periodic table, has a molar mass. Yeah, a molar mass of, what is it, 107.868 grams. All right. So now it just comes into plugging and chugging again. So our Q is equal to the mass of 1 mole, which we got from the periodic table of 107.868 grams. Our specific heat is still 0.24 joules per gram degree Celsius. And our change in temperature is just 1. So putting this into our calculator, we should get, do we expect it to be more or less than the previous problem, or than A? Less, right? Because 1 mole of silver has 107 grams, whereas this one here had 150 grams, right? So it should be less than 900. If you got something more than that, then you might want to check your work again. So doing that, we get 25. Let me put that into the calculator one more time. So 107.868 times 0.24 gives you 25.89 joules. And the units could be joules per mole. Okay. So what we just figured out here was the molar heat capacity, which is the amount of energy required to heat 1 mole of substance by 1 degree Celsius. All right, another scenario says it takes 1.25 kilojoules of energy to heat a sample of pure silver from 12 degrees Celsius to 15.2 degrees Celsius. Calculate the mass of the sample of silver. All right. What's one thing that we need to be careful about in this problem? Or in every problem, really?
The units.
Units, right? So it gives us 1.25 kilojoules of energy. What we're given up here, our specific heat is specific to joules, right? The units are joules per gram degree Celsius. So all of our units need to match up to those 3 units. So 1.25 kilojoules is equal to 1,250 joules. Right? Everything else, we can go ahead and calculate our delta T. So delta T is equal to our final temperature, 15.2, minus our initial temperature, 12.0. This gives us a delta T of 3.2.
So do we not have to convert to Kelvin?
No, because a change in 1 degree Celsius is equal to a change in 1 degree Kelvin. So like going from 0 degrees Celsius to 1 degree Celsius is the same thing as going from 273 Kelvin to 274 Kelvin. The change for each, the delta T for each process is still 1, right? So 274 minus 273 would give you a delta T of 1. 1 minus 0 gives you delta T of 1 as well. And like I said up here, again, the specific heat is not, it doesn't matter for what it is. So it could be joules per gram degree Celsius or joules per gram degree Kelvin. They're both equal to each other. All right. So.
Wait, you done with the last one?
Oh no, I'm still working on it. So Q our equation we should be using is Q equals MC delta T. In this case, they're asking us to find what? What variable? Mass, so that's M. So if we algebraically solve for M, so solve for M, you get M is equal to Q over C times delta T. If you plug everything you have into this equation, you should get M is equal to 1,250 joules divided by the specific heat, which we said is 0.24 joules per gram times degrees Celsius. And our change in temperature was 3.2 degrees Celsius. And putting this into our calculator, you should get 1627.6 grams of silver is our mass. Okay. So these are, question 58 is literally, can you use Q equals MC delta T? If you're able to solve these by yourself, then you're probably set for any other Q equals MC delta T problems that are this basic at least. They get a little bit more complicated as we go on. Who has the PDF with them right now? Anyone able to access that? Okay, so how about y'all go, or whoever has it, look after question 59 and everything past it, and you can pick a problem that you want us to go over, or you want me to go over. Yeah.
Why is the B mole at the bottom?
Why is what?
On B at the end. Let's change it to mole.
Because I just said it's the amount of heat that was associated with heating 1 mole of substance, but technically, I guess our units shouldn't be in joules, right? But this could also, this is the same number as the specific, what is it? The molar heat capacity, which is the amount of heat required to heat 1 mole of silver by 1 degree Celsius. So if you wanted a different unit for C, it would be molar heat capacity is equal to 25.89 joules per mole times degrees Celsius. So this number here is equal to that. It's just another constant for silver. Not that that's important. Did anyone say anything in the chat, Rich? Let's see. Any problems you want me to go over? No, crazy. Okay,
Well, I want you to go over all of them.
okay. Well, we don't have time to go over all of them. We have 10 minutes.
Pick a problem, any problem.
Maybe
Number 62.
62. In a coffee cup calorimeter. Crazy. We already did this one actually. I know we already erased it, but we already did it. It's on our YouTube channel, so I wouldn't want to take time off of people's life that already did this. So how about we do number 61?
It's the same type of problem, so nothing gained, nothing lost.
Yeah. And if you want to see 62, go on our YouTube channel and subscribe. All right, I'll give you 3 minutes to work on 61. This one's a hefty one. This is a fun one. They're little puzzles to me. Think of them as puzzles when you're studying, not as things trying to tank your GPA. So if you're stuck, start maybe just identifying what equation you should use in this problem.
Remember the golden rule of calorimetry, the Q of one thing equals the Q of another thing. Or negative Q of the other thing.
The golden equation for finding the final temperature. M1C1T1 equals M2C2T2 over M1C1 plus M2C2.
I like my way better.
The nasty man. Yep. Yeah, I'll pass on. All right, 1.5 minutes to go. We didn't go to biryani pot, bro. Yeah. Sam's been craving. Do this problem. So if you're not sure where to start, maybe you can just identify what's losing heat or what's losing energy and what's gaining energy. If you can do that using a plus and minus sign, I'll try that and work from there. So the thing that's gaining energy would have a plus sign and it's equal to the thing that's losing energy denoted with a negative sign. Probably like Rich said, is the most basic principle of calorimetry that you should be utilizing in a lot of these problems.
Like pretty much if you know that, the rest of the problem becomes pretty simple. It's just plugging in numbers.
And manipulating variables. All right. So if you took that advice, let's go ahead and identify what's losing heat and what's gaining heat in this problem. What do we say is losing heat? Nickel, the metal, right? So the negative heat, and we denote something that's losing heat with a negative sign, right? It's losing heat, nickel. So the heat lost by nickel is being gained by what?
Water.
Water, right? So I'm putting this as number 1 and everything in the water would be number 2. So Q, H2O, this is our second thing. So if you were to, we also know that the Q of anything, the heat associated with something of a process is Q equals MC delta T, right? So MC delta T. And using those two ideas, we just plug in these variables for each Q. We should get something that looks like this. So Q of negative M1 C1 delta T1. I'm putting the 1 here because we're talking about the nickel. Is equal to the heat gained by the water. So M2 C2 delta T2. And again, the way I just got this is just saying, okay, well, the Q is equal to MC delta T. So we just substitute this Q for the MC delta T. All right. What we're looking for is the mass of the nickel, right? So the mass of nickel is this one right here. So this is what we want. So we're looking for that. So what should we do? We should solve for that, right? So multiplying both sides by -1 would give you, I'll just change the sign, so you get M1C1 delta T1 is equal to negative M2C2 delta T2. And isolating for the mass of the nickel, which is M1, would give you this. So M1 is equal to negative M2C2, this guy, T2, over C1 and delta T1. And again, I put the numbers here because we have to remember that this top part is talking about the water. So I put a 2 here for the water side, and all the ones are talking about the nickel. All right. So we don't
Really,
want,
you could call those things whatever you want, like A, B, or like, it doesn't matter.
all right. So we have, let's see what we have. Let's identify everything that we have. So we have the specific heat of the nickel, which is C1. So this is C1. Water specific heat is what? So C2 is equal to what? Say it with your chest. I hear it.
Wait, say again, I'm sorry.
What's the specific heat of water? 4.184. Yeah. Thank you, Sydney. 4.184 joules per gram times degrees Celsius. So that's C2. The mass of the water was right here. So that's M2. And so we have M2, C2, C1. Now we just need delta T for each part, right? Delta T2 of the water and delta T1 of the nickel. So it tells us, we can do that up here on the left side. So delta T1, that's for the nickel. The original heat of the nickel was 99.8. And its final heat, or its final temperature was 25 degrees Celsius. So it's going to be final minus initial. So 99.8, which should give you, I don't know why I put that there, sorry. Negative 74.8 degrees Celsius. This is our delta T1. And our delta T2. The final temperature of the water was 25 degrees Celsius as well, right? Because they've reached an equilibrium. And the initial temperature of the water was 23.5 degrees Celsius. This should give you a change in temperature of 1.5 degrees Celsius. All right, so this is equal to delta T2. And if you break the problem down into its components, you see you have all the variables needed to plug into this to arrive at your answer of the mass of the nickel. So just plugging all that in, you should get 150 grams of water. We can't forget about our negative sign, which we'll put it right there. Specific heat of the water, 4.184. You already know the units for that. And the delta T2 of the water was 1.5 degrees Celsius. All over C1, which was the specific heat of the metal, which they give it to us as 0.444. And you already know the units for specific heat. And the delta T of the metal, which was negative 74.8. All right, you can do that. Just putting it into your calculator. Use parentheses when you put it into your calculator. Will save yourself headache if you can't find the answer key or answer choice on the test. So this is equal to M1. And when you put that into your calculator, you should get about 28.3 grams, which is our mass. So M1, or the mass of the nickel, is equal to that.
Also think about if your answer makes sense after you do it, like, obviously here you got a positive mass, which is what you expect. Like, like, what's it called? You'll never see a negative mass, like, notice here you have the negatives and negatives cancel out top and bottom, so that's kind of a check, make sure you're doing it right. So that makes sense. Also, if you don't get one of the answer choices, you probably did something wrong. So, yeah.
All right. So that took about 12 minutes for that one problem, but hopefully you get to a point where it doesn't take you that, I took that extra time because I wanted to explain it thoroughly, so that way you can understand it. But on a test, hopefully this problem doesn't take you more than 5 minutes. Okay? And like I tell them, everyone always, before a test, play to your strengths. If you study this type of problem and you still can't get it the day of the test, and it comes up on the exam, skip it and go to the next problem. You know, you don't want to waste half of the time of the test on this one problem when you could have been spending the rest of the time answering other problems and getting other problems right. Okay, so play to your strengths. And with that, I don't have anything else to say. Y'all are free to go. If you have any questions, we'll stay back for 5 minutes. And see you on Wednesday. At what time, Rich?
Thursday, actually, at 3 p.m.
Sorry, I'm still stuck in last semester schedule. Already more than halfway through this semester.
I got a pretty simple question. So we're doing like, I guess, what's it called? Calorimetry?
Yeah.
It's negative C, right?